now to something a bit more complicated. That's the timer management. Timers, you will see, we need timers at many different situations. Timeout, I mentioned this already, for retransmission is one of the reasons. So TCP uses different timers, for example, for these retransmissions. The question is, how do we select these timers? Well, for retransmission, for example, imagine you have the situation that you say, okay, there's a packet, we've sent it out, and now how long do we wait before we will trigger this retransmission? So we have this situation, you send your data from one computer to another. So how long do you wait here? Well, if you say, okay, maybe I need their acknowledgement here, that obviously is too early to resend the packet here. Because even if I immediately answer, due to the runtime, it takes some time. Okay, that's a stupid idea. If you wait until here, well, then maybe you're too late. Because something happened. Someone destroyed the packet. So somehow you have to find out this point. Okay, looking at the picture, it's quite obvious. So precisely this point, that's our round trip time. Okay, round trip time from sender to the receiver and back. Maybe we add a certain delta here for calculations, etc. So a bit more than the round trip time. So maybe 1.5 times the round trip time. Okay, but the problem is, yeah, that's nice. So round trip time, but what is the round trip time and how do I actually find out the round trip time? So somehow we should estimate this. On the link layer, that's relatively simple. Why? Remember, link layer, we have a computer here, for example, a host, we have a cable, and then we have a router. So the cable has a certain length, let's say 100 meters. What could happen to the signal here? Okay, we have here network interface cards, so maybe they buffer a bit, but typically the round trip time, the probability, it's quite narrow around a certain number here, 20. So if we pick round trip time somewhere here, so in our case maybe 26, that's a good idea. Okay, but on the transport layer, it's way more complicated. You have many fluctuations. You have a whole network, and maybe the network is a bit congested. Maybe the router takes a bit longer. Maybe you have different paths. And that actually smears out this probability somehow. So what to pick? Obviously, T1 is a bit too small, because you see the majority is somewhere here. Maybe T2 is too large, because yes, we actually, that this is larger than the typical round trip times, but maybe it's too large and we cannot react fast enough. The problem is that the round trip time varies in real networks. Just to give you an example, so shown here is the round trip time, measured round trip time in milliseconds, and you see sample round trip time here in red. What is our round trip time? Yes, we can flatten this, can calculate floating averages, something like this, but still, it's a question, how do we estimate this? So maybe we measure the time from the transmission of a segment until we receive the ACK. Okay? Yes, this is our sampled RTT, but this varies. As you see, we have all these spikes here. So sometimes we have round trip times here close to 340 40 milliseconds, but typically we are rather at, let's say, 135 milliseconds. So what should I take? 340 or 135? So we have to smooth it somehow. So it's quite common that we use many measurements, not just the current sampled RTT, and then somehow we calculate this estimated round trip time. An example shown here in green, some floating average. And this is exactly where an algorithm from Van Jacobson comes into this. So we have a way of dynamic calculation of the round trip time, and this is used then to adapt our timers. I just want to show you how this can be done. And this is also something where you can really optimize a lot, doing many PhD theses, how you calculate the round trip time. So TCP manages a round trip time variable for each connection. Well, it's quite a lot to do, but we have this RTT, and the RTT is the best current estimation of the round trip time. So each time you send a segment, you start a timer, and you measure how long does it take before I receive an acknowledgement. So this is what we measure. And if necessary, I initiate a retransmission, that if I receive the acknowledgement before the expiration of the timer, so that means maybe situation got better in the network, then I check, okay, I measure this sample RTT from this very specific acknowledgement I received, and then I update this variable RTT, my round trip time. And this is done based on the formula as shown here. Round trip time is some factor, a smoothing factor alpha times round trip time. And typically we pick, for example, 0.875 as a smoothing factor. So we take into account the old value to a certain percentage. That's our old round trip time here. That's the old one. We smooth it a bit. And we take into account the new measured round trip time, the sample round trip time. 1 minus alpha times sample round trip time. And this is now our new round trip time. And then we can calculate our timeout. We should not really take exactly round trip time, so a bit more, and then we can discuss the beta. So for example, beta is 2. We could optimize a bit, go for 1.5. Maybe this is too low, so we retransmit too often, but that's exactly something where you can start optimizing. So overall then it looks like this. So we have the sampled round trip times. This is for each acknowledgement I receive. This is my sample. You see this can go up to 340, can go down to 135, etc. Then we calculate this estimated round trip time. And based on this, then we can actually calculate timeouts. Okay, so timeout, and you will see where this pattern comes from in a second. So retransmission timer, we still have problems. So we cannot react fast enough to sudden changes. And so you see there are many improvements again from Jacobson. So why not taking standard deviation into account of the arrival time? So that's something we can do. And then we can compute a smooth deviation of the round trip time following the formula as shown here. Again, we have certain parameters, and then we can calculate the timeout interval based on this. This factor, we can discuss this endlessly, was determined then experimentally, and this is quite fast and simple for calculation. So doing so, we can react better with our timeout values to take into account these problems of these peaks. And now you see how we follow. Maybe this is not aggressive enough, but sending too often performing retransmissions too often, this really puts a heavy load on the network. So now you see how we calculate the timeouts following this formula. But as I said, you can discuss this. What kind of, how you set the timeout, etc. You can change this, TCP will still work, but maybe the performance is not as good as you want. Okay, so how does it work? All this retransmission, just an example. If we transmit data, as shown here, you start your timer and transmit data, and you see, well, the timer was too short. Then we, well, actually retransmit already, and then we have the acknowledgement. The point is, this acknowledgement, how do we differentiate between the acknowledgement for the first transmission or the second transmission? Because the algorithm simply says, okay, I receive an acknowledgement, but I don't know if this acknowledgement, because it looks the same, it acknowledges up to a certain sequence number, was for the first or the second transmission. This is why there's yet another algorithm that says, okay, do not update the round trip time on any segments that have been retransmitted. Why this retransmission? That may create false values. So that's Kahn's algorithm, and that's quite simple and typically used. And how this then works together with the retransmission, I will explain when I come to the backoff. Because if a segment doesn't go through, typically TCP assumes congestion. And one thing, as I will show later, is then we have to reduce the data rate. But the other thing, and that's shown here, is, well, maybe we are a bit too aggressive with our timers. So maybe we should double here our timeout. So if we are too aggressive and the timeout is too low, we'll retransmit too early, increasing the congestion, increasing the load in the network. And we assume that there's congestion if we do not return the acknowledgement in time. Then we retransmit, but we should not overdo it. So that's one of the ideas, is don't update the RTT and the retransmitted segments, but we do this exponential calculation. We double the timeout on each failure, so we are not that aggressive anymore. Yeah, we do not retransmit that fast any longer, but if we retransmit too often, too fast, we increase the load in the network. So that's the idea, Kahn's algorithm. Besides the retransmission timer, we have 3 more timers in TCP. One of this is the persistent timer. What does it do? Well, you can in TCP, as a receiver, send a message with window size equals 0 to a sender, and this obviously stops the sender. Sender will not send anything anymore because it thinks the buffer is full on the receiver side. So window is 0. Okay, now what happens if then the receiver consumes the data, and then somewhat later the receiver sends a packet with window size equals whatever, 100, but you lose this packet. The sender will still think, oh, window size is 0, I'm not allowed to send. So if you lose this buffer release message telling the sender now you can continue sending some bytes, you will have a problem. And the persistence timer exactly handles this. So you start this persistent timer if you're not allowed to send anything. And if this timer goes off with the expiration, you at least try sending something, a test segment. So you can try sending a byte. And if you still get the message back, an acknowledgement with buffer is 0, okay, you start the timer again. Otherwise, you will get back a window, not 0, but something larger, then you know, okay, something was lost, and I can continue sending. So persistence timer is one of the timers. By the way, you can use this artificially, this setting the window to 0, not only because your buffer is full, but also if you know that you may experience a layer 2 interruption, like you go into a tunnel and you have no radio connection, then you can actually, if you know this, notice this, then already you can stop the sender, and then you can send again a packet after you leave the tunnel with a larger window size, and the sender continues sending without breaking the connection. There's another timer called the keep alive timer. So what happens if no one has to send anything? If it's inactive for a long time, the connection, then let's say after 1 or 2 hours, you can then have the timer just, checking if the other side is still living. If not, then terminate the connection. Well, not often implemented and disputed function. Then finally, there's the time wait timer, quite important. The time wait timer is needed during the termination of a connection. So after both sides have sent their FIN packets, you still wait for a certain time. So typically the double maximum packet lifetime to be sure that no more late packets arrive. So that means typically, even if you have a delayed packet, well after this time, you can be pretty sure that there will be no late incoming packet for this connection. Okay, now, one of the features of TCP is reliable transfer of data. Basic principle, IP is unreliable, TCP has to do something. What has to be done? Well, you transmit your segments, segment by segment, you use sliding windows, you use acknowledgements, as I will show, and if something goes wrong, we have to retransmit. We create for all segments we send a timer. We start a timer for the connection, retransmission timer. We send our data, and then we have to follow. Well, if we have a timeout, we have to retransmit. This has been done, so many timers to handle. When do we trigger our retransmissions? Timeouts, that's the common case. So if we have a timeout, or if we get acknowledgements telling us there is something missing. Okay, so for now, let's assume a simple TCP sender, just to show how it works. We ignore now congestion control, flow control. I will come back to this. We ignore duplicate acknowledgements. How does it work? Okay, so what is one of the events? We receive data from an application. What do? As TCP layer, we create a segment with a certain sequence number. So this is the data we receive. We create our segment. The sequence number is the number of the first byte here. Okay, that's then our byte stream, and that's our segment we want to send. Then, the first time we start our timer, and if the timer has a timeout, what do we have to do? Well, we have to retransmit the segment that caused the timer, and then we restart the timer. Okay, how often do we do this? Well, until we receive the acknowledgement. If we receive the acknowledgement, we are happy. It acknowledges, hopefully, unacknowledged segments, and we can then update what is ACKed, and we can start a timer if anything is still outstanding. So that's how it works, a simplified scheme. Here you have a simple code for this. Okay, so how does it look like? In our example, if everything is fine, well, we don't need retransmission, but life is typically not going that smooth. So typically if we send something we may experience a loss. This could be a loss of the packet itself or loss of the acknowledgement. For the host A, this doesn't matter. After a timeout, you have to retransmit and you send exactly the same again. Host B will notice this and say, okay, I received this already, send back the acknowledgement, and host A can then update its data knowing, okay, everything up to 99 has been received. The next byte that is expected by host B is 100. What else can happen? So, for example, I send my data, first 8 bytes, then 20 bytes. I get a timeout. That's maybe premature because there's an acknowledgement coming. Okay, wow, but just missed it. I already sent out it again. I trigger a retransmission based on this timeout. Okay, starting again my timer, waiting for this. But as I get the acknowledgement and also the next acknowledgement, everything is fine. So I don't care about this timeout again anymore because I have already an acknowledgement, even for more. And what does the host B do in this situation, receiving this again? That was not necessary, but it just happened. Well, it will repeat the acknowledgement. So TCP can handle these premature timeouts. Nothing bad happens, everything is fine here. And no one triggers here timeout any longer because we already received the acknowledgement. What else can we do? If we send now our 8 bytes again, we lose our acknowledgement for this. I send the next 20 bytes. I receive the acknowledgement. This is automatically an cumulative acknowledgement. So there will be no timeout for these 8 bytes sequence number 92. Because at this point we received already an acknowledgement telling us everything up to 119 is fine. And that includes these 8 bytes and the 20 bytes. So you see there are different scenarios where we can generate acknowledgements using timeouts. So what can happen? So for example, at the receiver side, the receiver gets in-order segments with the expected sequence number. So that's nice. And all the data up to the sequence number, everything has been already acknowledged. Okay, so why should I send back an acknowledgement? All data up to the sequence number is already ACKed. So it's basically a duplicate. Then I do not immediately send back an acknowledgement, but I delay it. So I wait for the next segment. If I have a next segment, I send back the acknowledgement then, because that's something new. If there's no next segment, then I send the acknowledgement after 500 milliseconds. Because otherwise maybe I get the same stuff 3 times. So if I get, that's another event at the receiver side, if I get also an in-order segment, expected sequence number, so everything is fine. But an other segment has still ACK pending, so I haven't sent the other acknowledgement, I delayed it. Then I immediately send back a cumulative acknowledgement, ACKing all in-order segments. So what does it mean? So there was something missing, here up to this expected sequence number. This was missing, I haven't ACKed another segment. Now everything is fine. I can actually send back the acknowledgement acking all the in-order segments. But there could be also out-of-order segments arriving. And now this is, for example, a segment with a higher than expected sequence number. So that tells me, oh, I missed something. I detect a gap. How can this happen? Well, if the network layer dropped the packet, I can easily receive something with a higher sequence number and telling me, oh, there's now a hole in between, a gap. What do I do then? I cannot acknowledge this out of order segment. So I cannot acknowledge this. Because if I acknowledge this, then this tells the sender, oh, everything is fine up to this out of order segment. No. What I do is I then duplicate the ACK. I repeat what I already acknowledged and again indicate the sequence number of the next expected byte. Why do I do so? The duplicated ACK in this case tells the sender, okay, some data of you went through the network, I received something, but still I'm missing something. I indicate the gap. So I tell up to this sequence number everything is fine, but there's something missing. There could be also a nice segment that fills a gap. And then I can send acknowledgement, again, cumulative up to the sequence number where everything is received in order, everything is fine. So that's the idea. So if you have received data here, then there is a gap somewhere, received a bit here, and you received a bit there. And if you now receive a packet that actually fills this gap here, then you can acknowledge everything up to this byte. You still have a gap here. You cannot acknowledge everything up to here. You can acknowledge everything up to here because you filled a gap in this example. So this is how this works. So ACKs always tell the sender everything is fine up to this sequence number. And that the sequence number indicated in the acknowledgement is the next that I should send. So what is the idea behind duplicate acking, duplicate acknowledgements? Assume a scenario where a host A sends the data, know already how this works with a certain sequence number, 8 bytes, and you lose it. Okay? Then within the timeout time for this segment, you start sending yet another 8 or whatever bytes of data. And what does then the host B do? Well, the host B will return acknowledgement. This acknowledgement shows two things. First of all, it shows we expect the next byte should have the sequence number 92. Exactly, that's what we wanted to send, but it was lost. That's the first aspect. And the second one is, oh, data is arriving from your side. So host A now knows, okay, something has been lost. So host B is still waiting for data, but we don't have a situation where no data goes through. So, and for the next segment, the same is true. So we send an acknowledgement. So we duplicate the acknowledgement or have it 3 times or whatever. And the idea is when we receive the same acknowledgement several times, then the sending side can conclude, okay, we lost just some intermediate segment, but there's no heavy congestion. And the reaction then, as we will see, can be different. Because if there's no congestion, why should I slow down? If I just lose one segment, this can happen. Then I will react maybe in a different way. I will come back to this. So some questions. So why is this retransmission time of such importance? And why is it so important to calculate a good value for the retransmission timer? And what are the basic parameters we take into account to calculate this timer? Reliability is a big issue because IP is not reliable. So how do we achieve this and what can go wrong? Because that's exactly the problem compared to IP, where we don't guarantee anything. Here we guarantee something and then things can go wrong. And we had the issue of the duplicated acknowledgements. So what does a sender learn by receiving duplicated acknowledgements?